Well, hello, chemistry team. Coach coming at you again. Let's take a look at bond polarity. Now that we've done Lewis and Vesper structures, you don't really need a Vesper structure for this. You just need a Lewis structure where you can tell whether something is a bonding group or a non-bonding group. If it's a bonding group, which is either a single bond, a double bond, or a triple bond, doesn't matter. We're going to treat them all exactly the same. It's just a region of space that contains either 2, 4, or 6 electrons. We're just going to look at those electrons specifically in between two atoms. That's what a bond is, right? It's that force that holds those two atoms together so they don't fly apart. I'm going to look at 3 different perspectives on that bond, all right, and get into what's called bond polarity, which effectively you can think of bond polarity as how are those electrons shared between those two atoms. Think of it like a tug of war with just 2 people. Right, just me and you. Here's the rope, and we have a couple little like those little red flags that show the center of the rope between the 2 people, right over the middle of the mud puddle that's there. Imagine those are the electrons. We started between us, and then I say go, and we start pulling, and I'm like, right? Do those red flags move closer to me, and you end up in the mud puddle, or closer to you, and I end up in the mud puddle? Do you rip the rope out of my hands? Do we like break even, and that rope doesn't move at all? Which seems to be a lot of tug of wars. If you ever done it, you're like, and it's just 2 minutes, 3 minutes, and that rope hasn't moved, and then somebody gives up, and everybody goes into it. I miss tug of war, so I was always the dude right in the front, man. More often than not, I'd end up in the mud puddle. You lose your footing. A lot of fun. So we are going to look at a traditional point of view of bond polarity and how those electrons are shared, like you would in high school or introductory chemistry. And then we're going to advance that a little bit, more of a general chemistry perspective of bond polarity as far as what's called percent ionic character. And then we're going to look at what is most common at the highest levels of research, where they just pop it in a computer, let the computer run the quantum mechanical calculations, Hartree-Fock methods, and all these kinds of things. There's all these fancy models that look at to solve the Schrodinger's equations for all the electron waves, and they get these beautiful computer-generated electron density maps that are color-coded and tells you what region's more negative, what's more positive, where more electrons are, where less electrons are as far as electron density. They can calculate bond vibrations and bond angles and polarities. It's amazing. We're not going to do it. In my class, we don't have the computer simulation power to be able to do it. But if you move on to get maybe a bachelor's degree, a BS in chemistry, maybe you can take a computer class. That wasn't available when I was a student, but now they have like computer chemistry, computational chemistry. Really cool. A lot of chemists run their whole careers never touching wet chemicals. Everything's computer generated. With the power of today's computers, it's phenomenal what they can do. But I do want you to be able to read one of these called electrostatic potential maps. Pretty tough to put on my exam because of the color coding and things like that. We've got 140 students or whatever. That's a lot of ink, people. So let's look at the traditional way first as a little bit of review, and then we'll move on. I don't know if we can get them all in one video, but we'll see. So if those electrons are equally shared, right, you're doing the tug of war and the rope doesn't move. They're exactly in between those two atoms. They have equal strength, and we'll talk about what that strength is in terms of electronegativity. You've heard that term, but we're going to define it officially. That's called a nonpolar covalent bond, and we'll define polarity in a little bit. If those electrons are shared but not equally, right? We're doing the tug of war, and maybe you're pulling the rope a little harder, and the electrons are getting closer to you and further from me, but we're both still holding onto the rope. We're still sharing the electrons, but not quite equally. They're a little closer to you and further from me. Well, that creates some electrostatic issues that affects the bond. So we're going to call that a polar covalent bond. Right? The atoms in the bond are feeling different electron densities. So one will be a little more positive, one will be a little more negative. When we talk about the terms called partial charges. They're not ions, but they'll have partial charges. And then say you're so strong that you just rip the rope right out of my hands and you take my electrons from me. Well, that's how we consider a traditional ionic bond. So those aren't even shared anymore. Right? They're transferred, and we call that an ionic bond. So that's the traditional simplistic look at it. In the real world, nothing's pure ionic, nothing's pure covalent. There's always a blending of both. That'll be the second way we look at it. So, hey, let's look at electronegativity. To get to the root of bond polarity, we have to have some concept of how hard those bonding atoms pull on those electrons, like if we're in a tug of war. What do we call that strength that we pull that rope? What do we call that strength that that atom pulls those bonding electrons, whether it's a double, a triple, or single bond? How hard does it pull those electrons towards itself? What's its attraction for those electrons? That's called electronegativity, which we've mentioned before, right? So I've seen several different things, but it's effectively attraction that an atom in a bond has for the bonding electrons, i.e. the pulling strength. Right? So the higher, and it's actually been quantified, the higher the value, the stronger its pull. Right? And the more likely the electrons will reside closer to it. Right? And it follows periodic table trends similar to electron affinity. So, higher values to the upper right. And we have numerical values for that. But if you look at the periodic table, well, we know fluorine, we're not going to include the noble gases. We know fluorine's the top of the heap, right, as far as electron affinity, wants electrons and whatnot. So these tend to have higher electronegativity values. These tend to have lower electronegativity values. So these babies pull those electrons to the point where sometimes they become anions, right? They can, if they're so strong, they just rip the rope out of its hands. So these have been tabulated, quantitatively measured, or estimated by Linus Pauling. I actually met Linus Pauling. I think it was in his 90s, right? The vitamin C guy. I think he got a couple Nobel Prizes too, chemistry and peace, if I recall. I haven't thought about him for a little while, but anyway. Electronegativity is more of a molecular property, not an atomic property, because it's in a bond, right? But it's a combination of atomic properties. Remember ionization energy and electron affinity. Ionization energy is the energy it takes to remove an electron. Electron affinity is the energy change of accepting an electron. So it's really, if you think of the ionization energy minus the electron affinity, that it's proportional to electron affinity. I'm not going to go through the calculations on how they determine electronegativity values. But the higher the ionization energy, the harder it is to remove an electron, the more it wants to keep the electron. The more favorable the electron affinity, the more likely it's going to take an electron, or is happy to take an electron, the more negative it is. So if we subtract the negative, we get positive. So a very high positive ionization energy wants to keep it. A very high negative electron affinity, it wants another electron. That combination gives you a high positive electronegativity value. So electronegativity values are all positive. And I mean, you look at 20 different textbooks, you might see 20 different values. So I just hunted around. I found different values here and there. I tried to find them out to 2 decimal places, but that's pretty tough. So this kind of represents kind of a periodic table. I just stuck some values in there. As you can see, fluorine's way up there, pretty wimpy down here at the really large metals. They get bigger going down. So they don't have a strong pull towards electrons. That's why they tend to form ionic bonds. And then fluorine loves to be fluoride, those kinds of things. So I'll provide this on my exams. Make sure you print this out for the homework and whatnot. But you don't have to memorize electronegativity values, although you could compare, nitrogen versus hydrogen. So you can see the ones to the far right tend to be higher values. So let's take a look and I'm going to show you how we can use these electronegativity values to predict whether a bond would be a nonpolar covalent bond. Very similar electronegativity value, same strength of the pull. A polar covalent bond where they're not the same, so one of them pulls a little harder, but the difference between them isn't so great that it becomes an ionic bond. And that's the third one, ionic bonds, where the difference between the electronegativity values are so great, it just rips the rope out of the electrons out of the other one's hands, right? So let's put those numbers up. I'll give you an approximate range for that. And again, this is just all review, I think, from high school and intro chem at this point. All right, here's the framework. Now remember, the real life has a lot of gray areas. It's not black and white like this. But when I teach intro chem, I like to give you a number so you know, is it polar, is it non-polar covalent, is it polar covalent, or is it ionic? So here's what I use. I've seen different things in different textbooks. That's okay. Go with whoever's grading you at the time. So what we're going to do is calculate the difference in electronegativities, the pulling strength, between the 2 atoms. There's only 2 atoms in a bond, right? So you're going to have one number minus another. You're going to pick whatever the electronegativity is for atom number 1 off this table and the electronegativity for atom number 2 off this table and subtract them. That's delta En, the difference between the electronegativity values. Now, we want this to always be a positive quantity, so we're going to take the absolute value of the electronegativity of atom number 1 in the bond, whichever one you define as atom number 1, minus the electronegativity of atom number 2 from this table. It's really easy. You can do a lot of it in your head, right? You just subtract the two. Boom, done. Now, so it doesn't matter which atom you do first or second, you'll get the same numerical value, just positive or negative. So if you take the absolute value, you don't have to worry about it. So who cares what order you put the atoms in? Yay for us. Now, here's the black and white numbers I'm going to give you, even though in the real world, there's no fine line between them. It blurs from one to the other. That's going to be the second way we look at it. So if the difference in electronegativity value is less than or equal to 0.4, we're going to call that a nonpolar covalent bond. Obviously, in like diatomic nitrogen or oxygen or any diatomic molecule, they're the same atoms. So you're subtracting the same numbers, you're going to get a value of 0. That's like a perfect nonpolar covalent bond. But, you know, it's still, even though we're pulling on the rope, it may move a little bit. It's still fairly equal, right? Equally shared electrons. So we're going to go up to 0.4. And the reason I like 0.4, that's pretty close to a carbon-hydrogen bond. So if you take the value of carbon minus the value of hydrogen, I think you get like 0.35-ish or something like that. All right, so if you look at hydrogen, which is a 2.2, carbon over here, what's it, a 2.55? So 2.55 minus 2.2 would you give you 0.35, rounds to 0.4. So about 0.4 in organic chemistry, a carbon-hydrogen bond is considered a nonpolar bond. So that's what I'm using as my breaking point between polar covalent and nonpolar covalent bonds. All right, that may be different for different professors, but for me, 0.4 is our magic number. Now, if it's greater than 0.4, now we're getting a difference in electronegativity, or the electrons are far enough away from one atom than the other, where you start to build up more negative charge on one versus the other. So we're going to call that a polar covalent bond. So if it's higher than 0.4 or less than 1.7. Once you get to 1.7, the difference is too big, right? They're not shared anymore. And I'll show you what these look like. We'll do some examples and show you what partial charges are in bond polarities. Now, if it's greater than 1.7, boop, in the tug of war, you just rip the rope out of their hands. So, and that's where you start. And you get those numbers where you have a lot of these metals over here with these nonmetals, really high values of nonmetals, really low values of metals. That's why they tend to form these ionic bonds. Right? So anything in and I've seen textbooks that use 2.0, whatever. That's okay. I try to use, the sodium chloride as a traditional ionic thing. So there's your numbers. Let's do some examples. All right, here's our first example. Let's take the carbon-hydrogen bonds in methane, CH4. Now, would you agree, if you drew the Lewis structure for methane, all the carbon-hydrogen bonds are the same. So you only have to do one calculation, right? This carbon with that hydrogen, that carbon with that hydrogen. You don't multiply hydrogen by 4 because there's only 2 atoms in a bond, right? So let's take all 4 bonds in methane, calculate delta En. So let's take the electronegativity of carbon minus hydrogen, or you can do hydrogen minus carbon, doesn't matter. We're taking the absolute value. So if you look on the electronegativity trends, carbon over here is a 2.55. Hydrogen over here is a 2.2, right? So let's take 2.55 minus 2.2. Limit, that's good to 2 decimals. That's good to 1. So we're limited to 1 decimal. So you get 0.35, which rounds to 0.4. But always look at the non-rounded value. Well, that's less than 0.4, right? So that would be considered a nonpolar covalent bond. So if we were going to draw that bond, right, you could pretty much draw the electrons almost equally between them. Or if we're just drawing a line. The thing about a line, it doesn't show you anything about polarity. If you draw the electron dots, you can draw them closer to one versus the other. So let's do one that the delta En is greater than 0.4. So let's say, the phosphorus chlorine bonds in PCl3. So what I want you to do, since now they're all going to be the same, right? Now, if you have a more complex molecule with multiple different bond types, you have to do it for each type of bond. But go ahead and find the electronegativity values for phosphorus and chlorine, if you have my electronegativity value printed out, and see if you can predict what type of bond you have. So I'm going to pause it, do it myself. We'll see if we get the same thing. All right, what did you get for your delta En? So let's look up the values for phosphorus and chlorine. So we're going to take the electronegativity of phosphorus minus chlorine, or vice versa, it doesn't matter. So you just look them up there. I can't see things backwards. So phosphorus is 2.19 right there, and chlorine is 3.16. Right? So I take 2.19 minus 3.16. If it's negative, make it positive. I get 0.97. Now, that's greater than 0.4 and less than 1.7. So that's a polar covalent bond, not equally shared. Now, who has the greater electronegativity? Chlorine. That means chlorine's pulling harder. Those electrons are closer to the chlorine. That creates a polar bond. Watch what happens. So if I was drawing the bond between phosphorus and chlorine, I would draw the electrons a little bit closer to chlorine, right? Or we can just draw the bond like that and represent it with the fact that now the electrons are closer to the chlorine. This is more electronegative. And that's less electronegative. Everybody agree? You can see the numbers. So what happens is as the electrons get closer to the chlorine, it picks up a negative charge. We call that a partial negative charge. Let me erase this polar covalent bond here. So that's called a partial negative charge. It's not a full anion, but it's on its way, right? As the electrons are getting closer to you, you feel more of a negative electrostatic charge, right? So the chlorine's pulling harder, not enough to pull them away, but it's building up that partial negative. Which also means the electrons are further from the phosphorus, so it builds up a partial positive charge right there. You see that? So this is a partial negative charge. That's a partial positive charge. And those values, we're not going to calculate them in my class, but if you do some of these computational methods, they can actually calculate those partial charges. And then what we can do is we usually use an arrow to represent the bond dipole. So now do you see it's like it has opposite charges on either side, so that's a dipole. Right? And we use a little arrow that points towards the more negative side to represent that bond dipole. Right? So it's called a dipole moment. So the arrow is a dipole moment. So the arrow represents the dipole moment. Right? And if we had a numerical value, it represents that separation of charge. So you could have two polar covalent bonds, but one with a higher dipole moment than the other. We won't be able to do that and calculate in my class, but you can kind of see how that works out. So that arrow represents the dipole moment, points towards the more negative side, right? Which relates to the polar bond. Okay, so it's a reflection of how polar that polar bond. So that's where the term polar comes from. You've got like a magnet, North Pole, South Pole, those kinds of things. But if it's electrostatic, you have a negative side, positive side, kind of battery. You got the negative end and the positive end. You can think of those as poles. Now, what happens if that breaks over 1.7? Now you get an extremely or extraordinarily polar bond, which we call ionic. Let's do that one next. Let's do the magnesium fluorine bonds in magnesium fluoride, which we would already look at that and go metal, non-metal, probably ionic, right? But some ionic bonds aren't quite as ionic as you would anticipate. So let's take the difference in electronegativity values. So let's take, now you can do fluorine minus magnesium or magnesium minus fluorine, doesn't matter. Let's look them up here. So magnesium is right here at 1.31. Fluorine is the top of the heap here at 3.98. So I did 1.31 minus 3.98, made the negative a positive. I got 2.67. That's a lot bigger than 1.7. So that would be considered an ionic bond for this particular way of looking at bond polarity. So now we can draw that. So we've got the magnesium and the fluorine, but the fluorine has effectively taken those bonding electrons away, right? So we're going to represent that with brackets. So that completes the octet on the fluorine and it no longer, it's not a, remember, if it was still shared, if it was a polar covalent bond, it would have a partial charge. But now it's a full anion, and this is a full cation, which is just the Lewis structure for an ionic compound. So it represents that those electrons have been transferred from the magnesium and the fluorine. That's how that works out, gang. Oops, let's put the 2+ on the outside there. I typically don't put brackets around the cation because there's no electrons trapped there. So let's take a look at a more advanced model. That's pretty straightforward. Let's take a look at a more advanced model called percent ionic character. That represents a little more reality. All right, in the so-called real world, there are very few pure covalent bonds like diatomic molecules or ionic bonds. I don't even know if there's a pure ionic bond out there. I mean, your best bet would be probably the highest and lowest values, francium fluoride. That's probably the most pure ionic you're going to get, but it's not 100% ionic. All bonds in reality are a blending or a mixture of some ionic characters, a little bit of sharing, a little bit of transfer, and some covalent characters, some sharing. It's a combination of both. So we reflect that mix of the two with a more advanced concept of bond polarity called percent ionic character. So if a bond is 20% ionic character, of course, it would be 100 minus 20 or 80% covalent character. So that's a better way to look at it rather than the electronegativity differences greater than 1.7 or less than 0.4. It's like, well, it's 15% ionic, 85% covalent. That's a better way of looking at it. Let me show you how to do that. All right, so what people have done is gone in the lab, taken known molecules with known bonds, and actually measured their percent ionic character. You could probably do it quantitatively well with computer models, and then plotted the percent ionic character versus delta En. So the percent ionic character depends, that's the dependent variable, on the delta En. So obviously delta En is not going to get much higher than 3 typically, and we get from 0 to 100%. So if you're way down, like I said, about less than 0.4, we treat it mostly as covalent, about 0% ionic character. And then it starts kind of trailing out. And what they did is they took a whole bunch of different bonds and just kind of plotted, and you got values here and there and all over, and they just kind of did a trend line through it, right, a best fit line. And so what you do is you calculate your delta En like we did before and just find it. So if your delta En is 2, you just move up the plot and look over and just kind of estimate, like you're reading some graduated measuring device, on what that would be. And you could probably go up in 5s, right? 50, 55, 60, 65, 70, 75, right? So you can estimate that's 55, 60, somewhere in the 60%-ish range, probably to the nearest percent. I don't think you'd be able to estimate to any, decimal places. So let's go to the nearest percent, maybe, 59, 60, 61, 62. And if you're within 3, 4, 5% of mine, I'd probably usually pretty good at the end, plus or minus 3% on either side. Because my lines obviously aren't perfectly straight. I didn't have a ruler on me. But you just find your delta En, go up and over. Now, obviously, nothing really ever hits 100%. It can't happen, right? It's not going to happen. But we could get 0 for a lot of those diatomic molecules. And so I just kind of photocopied this from a plot that I saw. So this is what I'll give you on an exam, right? It's just a junker plot. So this is where all the different molecules were. You can see the data points from the lab. So this is the trend line. And you can see my ugly markings here, trying to go every 5% here and working through my electronegativity values. And you just kind of delta En, go up and over, estimate it to the best of your ability. So let's do a practice one real quick. All right, let's do your prototypical ionic compound, sodium chloride. So what's the percent ionic character for the bonds in sodium chloride? So go through and calculate your delta En, electronegativity of sodium minus the electronegativity of chlorine, or backwards. You're taking the absolute value. So you just look them up. So sodium's a 0.93. Chlorine, where's chlorine? Right there, 3.16. So just take the 0.93 minus 3.16, make it positive. So I get 2.23. That would qualify in our other model as definitely an ionic bond, right? But now let's look on here. And this is just kind of rough drawing. So you would just look on it on your chart here, find 2.23, right? So here's 2, find 2.23, go up, go over, and estimate it. So let's break this up here. So this would be 2.5, right? That'd be about 2.5. So 2.23 would be right about there. So if we took a ruler and went up, boom, 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 to where it landed on that plot, and then take another ruler and come across, right about there, give or take, it's just an estimate. So if we look on this, 50, 55, 60, 65, 70, that looks right around, I'd say that was around 70% ionic character. You would think it should be 100%, but it's not. So sodium chloride is about 30% covalent, 70% ionic, give or take. I put the decimal there because we're good to the ones place. So it's just a real simple extension to what we've done before. We could label that as an ionic bond because it's got a delta En greater than 1.7, but it's about 70% ionic character. Pretty simple to do. Just give me the best estimate you can off the table, off this chart. I will give you that on my exams, even though it's ugly. I haven't bothered to plot that one yet myself. So let's look at the last and probably the best concept of looking at bond polarity, electrostatic potential maps, which will be very difficult to do, but I'll do my best job. All right, what are electrostatic potential maps? These are things you're going to see in your textbooks a lot, especially on computers, right? You might take a computational chemistry class where you actually generate these, where you just plug in the parameters and it does the quantum mechanical calculations for you. And it gives you a color-coded image, right? So it's an image of the bonds, right? And the two atoms in the bond, we'll do molecules later. But it reflects where the electron density is. Are there more electron-dense regions and less electron-dense regions? Obviously, if you have more electronegative atom and a less electronegative atom, there's more electron density near the more electronegative atom and less electron density near the less electronegative atom. And we reflect that with colors generated. So I have to talk about what those colors are. So let's do a little theoretical experiment. Imagine the end of your finger is a positive point charge. And take the molecule, or in this case, the bond. We'll do molecules later. So you got the two atoms. Take this positive point and go one, 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 like a magic fairy wand, all around it. And that positive region is going to sense electron densities. It's going to be more attracted to higher electron density regions and less attracted to less electron density regions, right? Because you have more negative and more positive regions. So this point charge is going to be repelled by the more positive regions and more attracted to the more negative regions. How do we color code that? Let's look at that next. You're just scanning it all over the place and you get color codes from it. When you look at electrostatic potential maps, you have to know what the colors mean. So if you just want to memorize blue areas, tend to have less electronegative, less electron density, so they tend to be more positive regions, fewer electrons. Red areas are more negative regions, higher electron density. So red, more negative, blue, more positive. Why is that? Okay, so if you do the rainbow, red, orange, yellow, green, blue, indigo, violet, we know from electromagnetic radiation, red is lower energy, and it goes all the way up to violet. So blue is higher energy, red's lower energy. So if I have that imaginary positive point and I move it around, well, if there's another positive region, that's going to have a high repulsive energy, high energy blue. So that's a positive region. If I move over to this side and there's a low electron density, a high electron density, it's negative, that's going to be more attractive or lower energy, okay? So regions that have high electron density are attracted to that point particle and will be the lower energies, whereas regions that have low electron density or are positive are repulsed, high energy repulsion from that positive point. Or just remember, blue is a positive region, red is a negative region with varying colors. I don't have a yellow. Yellow would be in here. I don't have yellow pens, but in varying. So if you see a lot of this, that means it's a little more of a true nonpolar covalent bond. The more red, the more blue you get, the more polar it is to the point of ionicness. Is that a word? Oh, let's look at one. All right, so just a quick, and hard for me to give these to you on exams and quizzes, but you see them as examples in textbooks and on websites all the time. So here's varying degrees, what we would consider an ionic bond, polar covalent bond, and nonpolar covalent bond, prototypical, right? So if we look at the traditional ionic, we know the chlorine's way more electronegative. So you've got this more negative region there, higher. So you can see it's bigger. It's got more electron density around it, whereas the sodium has lost the majority of the electron density. So this is more positive. So if you take that point particle, it's going to be a more positive region, so repelled or higher energy. Whereas it's going to be that point particle is going to be more attracted to the negative region, so it's a red or lower energy, and you got this big bulbous region. It's more, and if it became ionic, it would separate out into like two bubbles, right? Whereas HCl is still polar, but not quite as ionic. So see, it doesn't have that pinch in here, right? If it's ionic, that would pinch off, but just like boop, pinch between them. So it's still polar, but it's not approaching the ionic amount. So the more ionic it gets, the smaller this gets, the bigger this gets, until it just breaks in half. And if you have a nonpolar covalent, like any diatomic molecule, you're not going to have any reds or blues. There's no distorted polarity. The electron density is pretty much the same everywhere, so it's kind of the yellowish green all around. So we'll do this for molecules later, but there's your intro to electrostatic potential maps. Yay!